Okay, so last time we had a case study, we looked at Poisson regression, where we were trying to predict the number of roadkills using various predictors. But now we're going to look at one where we're going to have to do a Poisson rate regression. So Poisson rate regression we often use where we have something like distance or time, or as you'll see in this one, the number of policies that's going to affect the number we'll see. So we're sort of going, let's predict the rate per unit. That's probably not the best explanation, but let's go and have a look and see if I can explain a bit better. So we're looking at some insurance data. So we're reading our packages and we're reading this data. What we see here is we've got different districts, we've got engines, so it's basically insurance claims for cars. We've got information about the engine, about the age of the policy owner, the number of policies and the number of claims. And what we want to do is predict the number of claims. Our response variable is the number of claims. So first of all, I've discussed this with a couple of you. I will normally see these as character and convert them to categorical for you. But I like to be really precise. With mine, I've actually said, look here, wherever there's a column that's a character, I'm using the across function. I want to mutate, so I want to convert that column into a factor. So being really precise, the first three predictors we've converted to categorical variables. So let's do some exploratory data analysis. So we'll have a quick look at the response variable, which is the number of claims. Very right skewed here. So definitely thinking that it's not normal. Sum of distribution, we're counting the number of claims. That's a non-negative integer. So you should be, first of all, thinking about Poisson. If we look at policies versus claims, you can see there's a strong relationship. As in a particular strata, we have more policies than we have more claims, which makes sense. So we need to take into account the number of policies in our model. So the next thing I'm going to do some grab all the factors, do some pivot longer, blah, blah, blah. You've seen me do this before. What we're looking at here is just the number of claims versus the various predictors. And this is the problem with just looking at claims. You can see that, 35 plus seems to have a lot more claims. This particular district, this particular car are the ones that have the most claims. And you go, okay, so that's fine. But what about if we say, well, let's look at the proportion. So we're looking at the number of claims per policy and redoing the plot there. Suddenly things change. The reason we had more claims in the 35 plus is they have more chance, because they usually have more stability in their career, to buy insurance. There's more policies. Now it actually it changes. The higher proportion of claiming is the under 25s. The districts don't seem to have a lot of difference, and you find the bigger cars are more likely. So we have to take into account, it suddenly changes the patterns we see once we take into account the actual number of policies. So how are we going to deal with this? Well, we're going to do a GLM. First of all, we are going to set it into a Poisson, so we're doing a Poisson regression. We've got the thing we want to predict is claims. We've got district, engine, and age. But we've got this extra term here, offset is log policies. And if you remember that function, what we're doing is we're saying that you've got the number of claims divided by the number of policies. We're looking at the log of that. And then when you rearrange it, all you're doing is you're adding a predictor in there, and the predictor will be log policies. But the thing is, the coefficient associated with that is forced to be 1. That's all it does. So when I actually run this, you don't actually see policies in there. It's disappeared because there's no point me telling you what the estimate is. The estimate is forced to be 1. You only know about it because up here it says it. So this is taken into account. So if there's more policies, you're going to get many claims, but it's been taken into account automatically in the model. So we can have a look and see what's significant here. We've definitely got district is significant. District 4 is significantly, in this case, higher than district 1. The engines, the bigger engines are significantly higher than the smaller engine, and the ages. We could say, well, how good is this model? So we could do our usual look at our residual deviance. So here's our command that we do for that. Pretty good, 0.57. So, rough rule of thumb, if that was a number, a p-value less than 0.05, I'd say my model's not good enough to explain everything. Because it's greater than 0.05, it's good. That's a pretty darn good model. Now, we've done a ANOVA before for checking two models. The other thing is you can just put a single model into ANOVA And what it's really good for, as you'll see here, is asking about those categorical predictors. So here you can ask, is there, a significant difference between District 4 and District 1? But what if you wanted to ask the question, is district a significant predictor? Well, then you use the ANOVA command. We do the ANOVA command, and we can say here, yes, this is less than 0.05. So, in fact, all of them are significant predictors. That's all really good. So, what's next? I'm going to try something different. I want to explore this idea that we've got this coefficient there, which is log policies, and we set it equal to 1. So the question might be, well, maybe it shouldn't be 1. So there's two ways we could look at that. The first thing I'm going to do is I'm just going to put it in here as a predictor. So according to me, we've used an offset. We're saying the coefficient should be 1. So what I'm going to do is I'm going to take it out of the offset and put it in as a predictor and say, well, what is the coefficient? And as you can see, it's 1.2. It's pretty close to 1. In fact, if you use the standard error 95% confidence interval, 1 is a good option. There's another way we could test that rather than just sort of looking at this and eyeballing it and saying, yeah, that's about right. What we could do is we could put in log policies and offsets. That gives us a coefficient of 1. Then I'm going to add an extra predictor of log policies, which is going to be the extra bit that's not already done in the 1. So it's almost like I've taken it and I've split it into 2 bits. I've got one bit of the log policy which is set to 1, another bit which is going to be set to what's left over. And hopefully that's going to be close to 0 because the 1 is enough. So let's run that and have a look at it. And yes, we are. Here we're saying it's only 0.2, which we got from before. Is that close to 1? Well, yes, the p-value is large. It's not significantly different from 0. So it's a quick way of me going, actually, setting the coefficient to 1 was pretty good. I did it based on the idea of the model, but I can test using the data. This is a good thing to do. So we've got this model. It's got district, engine, and age as predictors. We're going to have log policies as an offset, so that's a coefficient of 1. So let's have now a quick look at our residuals. So we're going to grab our Pearson residuals. We're going to grab our fitted. And then what can we do? Well, we could look at our model versus each individual. So what I've got here is I've got my residuals versus claims versus fit versus policies. So you can see it's all looking pretty good. So this is all my continuous. It's a bit squashed up. So all I've done is I save this as a P. And now if I go P plus log, so you can see there's pretty well random scatter. I've got my residuals versus the number of claims, my residual versus the number of fits, and my residual versus the number of policies. All pretty good. That claim's a bit rubbish actually. I don't know why I put that in there. I think it's got to do a quick code. Next thing I'll do is I'm now going to do it versus all my categorical predictors. And again, what do we want to see? We want to see that this line y equals 0 goes between all the box plots. So it's all looking pretty darn good. So there's some notes here, you can go and look at it, but basically this is our final model. We take the number of policies and we times it by, and our model is giving us the adjustment. It's almost saying what proportion of those policies will give you your number of claims. So, pretty good model. There's your first offset. When do we use offsets? Any time where we think there's some sort of thing we've measured that as that increases, you're going to get more of your response variable. So, time, space, and in this case, policies. Okay, that's it. Next week, we're going to do some case studies. It's going to be all case studies, but I'll chat to you next week. See you then.